Oh, hello there. I'm Bilchen, a cute bear.
Hey there. I'm Nimikung, a cute bear. And this yellow one here is the drooling snack stealing impatient kiddo-chan.
It's Genevieve Angelin. Don't make fun of my name.
Okay, sorry. I won't say it again.
You can say it. It's just a joke. Hang in there, Nimmer.
Aw.
So, what are we doing this time?
This time we're going to delve into the equivalence of equations.
S.
Yeah.
Aw. Equivalence might sound difficult at first, but essentially it's what we've discussed before. Ben Chan wasn't here for that. Are you okay?
I've reviewed the previous video, so I'm good.
Impressive. Let's start with that recap then. So, Fen-chan, how would you solve this equation?
On this expression, transpose 2, transpose 3x, and then divide by the coefficient of x, which is 2. And we'll get the value of x.
Right, so why can you find the solution to this equation by that?
Because all these equations, which have the same solution, are like shadow clones of Ninja. Once we get to this final equation and know its solution is 3, we also know the original equation's solution is 3.
Exactly. You've got it.
Hee hee.
Oh, Nimikun is blushing just like you.
Hee hee.
Why are you blushing now?
RR. And so, the relationship between equations with the same solutions, which we referred to as clones last time, is called equivalence in equations. These 4 equations are all in an equivalent relationship.
So equations with the same solutions, these shadow clones, are called equivalent equations.
Yes, that's right.
I see, so equivalence is like the formal term for shadow clones.
Exactly. That's the idea. Now, Nimikong,
Yes.
are these 2 equations equivalent?
If 2 equations are equivalent, that means they have the same solution. So if I find solutions for both, would that work? This one's solution is 3 times 4 equals 12, so x equals 4. For this equation, when x equals 4, the left side is 3 times plus equals 17, and the right side is 0 plus equals 17, which makes it 17 equals 17. So x equals 4 is the solution. Thus both have x equals 4 as the solution. Are they equivalent?
Well, your general approach is good, but there's a significant issue.
What's that?
Even though for both equations, the equation holds true when x equals 4, can you be certain that there are no other solutions?
Right, equations can have multiple solutions. For instance, with my explanation, one might have solutions x equals 4 and x equals minus 1, while the other only has x equals 4 as a solution.
So even if x equals 4 is a solution for both, that alone doesn't come from their equivalent.
Exactly, it doesn't.
Why is that?
Firstly, an equation for x is a statement that can be true or false depending on the value of x. To solve it means to find all values of x that make it true. Got it?
I got it. I saw it in the previous video.
Oh, good job, Ben-chan. Another way to put it is that an equation is essentially defining, among all the numbers, a group of numbers that satisfy that equation.
Is this group composed of all solutions to the equation?
Exactly, that's right.
Earlier, you took that if we can find all solutions, we fully understood the equation. Is this related?
The solutions to an equation for x, in essence, are values of x that make the equation true. That is, this group of numbers. Alternatively, an equation can be seen as a condition that determines if a number belongs to this group.
Oh, this group is a collection of all the solutions to the equation. So the equation holding true with the value of x is same as the value being a member of this group.
That's right. So, if this equation holds true when x equals 4 and x equals -1, the group of solutions to this equation looks like this. But if this equation holds true only when x equals 4, the group of solutions to this equation looks like this. So the group of solutions, a key property of equations, is different.
I see. Because the group of the solutions the equation determines is what really matters for it. The equations sharing the same core are equivalent, aren't they?
That's right.
If what the cute bear liked to eat is what really matters for the bear, the cute bear who don't like octopus and can't eat takoyaki if not equivalent to cute bears in Osaka.
You're totally talking about me. Don't spill the beans.
Or so to recap the conclusion, to verify that these two equations are equivalent, it's not enough to just check that both equations have a solution like x equals 4 in common. We must ensure that the entire group of solutions is the same.
I see.
Moreover, if you just want to know whether these two equations are equivalent, there is a simpler way.
How, sir?
If there is some value of x, like x equals question mark, and if this equation holds true for that value, then for that same value, the calculated value of the left side should be equal to the calculated value of the right side. And if they're equal, then adding the same value of 5 to them should also make them equal, right?
Well,
I see.
What I just said in the case of these two equations is that the values that make this equation true, meaning the solutions of this equation, will also make this other equation true, meaning they'll also be solutions of the other equation. That's what it means.
well,
I see.
Or
that's like what we discussed earlier. In terms of this kind of diagram, if this equation is true, then this other equation is definitely also true. So compared to the group of solutions of the first equation, the group of solutions of the second equation would be larger. Right?
us. That's impressive.
Oh, what do you mean?
That's why. If this equation holds true, then this other equation will definitely hold true as well. So if some value makes this equation true, it should make the other equation true as well, right?
Then here.
So, the values that are solutions for this equation are also solutions for the other equation, right?
Then here.
For the first equation, the numbers that belong to its group of solutions for the second equation should also belong to its group of solutions, which means this group of numbers completely fits inside this other group of numbers, right?
I see. Van-chan, you're amazing.
Hee hee.
Hee hee.
Why are you blushing now?
Or also, like we see now, if this equation holds true, though their equation also necessarily holds true. Then the first equation, for the second equation, is said to be a sufficient condition if the first equation holds true. It's sufficient for the second equation to be true, that's the nuance.
In other words, the condition not sufficient has a narrower range in which it holds true.
Yes, exactly that. Similarly to now, we assume that if the first equation holds true, the second equation also necessarily holds true.
The situation hasn't changed, right?
Exactly. In that same scenario, the second equation for the first equation is said to be a necessary condition for the first equation to hold true. It's at the very least necessary for the second condition to be true. That's the nuance.
So, because the range in which the first equation holds is narrower, for a number to be a solution to the first equation, it obviously has to fall within the range of solutions for the second equation, right?
Exactly. You both are getting it.
Hee hee.
Hee hee.
Hee hee.
You don't need to say it twice.
Or, so to sum it up, if the range where one equation holds fits completely within the range where the other equation holds, the one with the narrower range is the sufficient condition, and the one with the wider range is the necessary condition.
I see.
It's been organised really well.
So originally, we were checking if these two equations were equivalent, meaning the range of solutions for both equations was the same, right?
Oh yeah, that's right.
If that the first equation holds, implies that the second one also holds. Then the range where the first equation holds fits completely within the range where the second one holds. So, if that the second equation holds, implies that the first one also holds. The range where the second equation holds fits completely within the range where the first one holds. So, then we can say the range where both equations hold or the group of solutions matches perfectly, right?
Fan Chan, you're amazing. Exactly right.
I see. If the group of solutions for the first equation fits perfectly within the group for the second, and the group for the second fits perfectly within the first, then the two groups must overlap perfectly. Way to go, Fan Chan.
Hee hee.
Hee hee.
Hee hee.
You said it twice.
I just did okay. Let it go.
Or, in the case of these two equations, if the second equation holds, in the situation where 5 is added to both sides, the left side and the right side would be equal, so they should be equal even without heading, right? So the first equation also holds.
I see.
To sum it up, all of these are saying the same thing, and all of these are also saying the same thing. As for the current two equations, coincidentally, they satisfy condition A, and they also satisfy condition B.
So they're equivalent when that's the case.
That's what it means. And then, to verify if two almost identical equations are equivalent, we should check. When the first equation holds, the second one must also hold, and when the second equation holds, the first one must also hold. If these two conditions are met, you don't actually need to find their solutions.
Oh, I see.
By the way, if they are equivalent, they satisfy condition A and they also satisfy condition B. So the first equation is both a sufficient condition and a necessary condition for the second equation. So combined, it can be said that it's necessary and sufficient.
So, are the terms necessary and sufficient condition and equivalent synonymous?
Yes, exactly.
If they satisfy condition A and also satisfy condition B. The second equation is both a necessary condition and a sufficient condition. So can we say that the second equation is necessary and sufficient for the first equation?
Yes, that's also correct. If one is the necessary and sufficient condition for the other is definitely the necessary and sufficient condition for the original one.
If so, since equivalent and necessary and sufficient are synonymous, if one is equivalent to the other, can we also say the other is definitely equivalent to the original one?
Exactly. They are mutually equivalent or mutually necessary and sufficient is another way to phrase it. Terms like equivalent or necessary and sufficient mean that the solution groups of the two equations match perfectly. It's obvious when you think about it.
I see.
I really get it now.
Next time we'll delve into how to specifically transform equations to be equivalent.
I'm looking forward to it.
Don't sneak any sacks.
I don't mean that.
Or